Okay, welcome to lecture 1 in module 2, which is just done asynchronously in lieu of a live class on January 19th. What we're going to do is talk about Python and how it's going to be used for calculations and data analysis in the class. You'll sort of see that there's so many different packages and tools that are already available for us that it's really going to help streamline our analysis, even sometimes more straightforward than using a spreadsheet to do certain types of calculations, especially when we get into optimization and that kind of thing. So we'll just talk a little bit about Python in general, and then we will solve our first problem. So this is a single reservoir meeting a constant demand, not unlike the system that was discussed in unit 1-1. So in this class, we're really going to be using Python as a tool. You know, there aren't going to be test questions about Python. It's not going to be like there's learning objectives about Python itself, but rather it's going to be used, you know, to help streamline our calculations. And you'll see that a lot of the sort of technical stuff is going to be provided for you in these kind of prototype functions that then you're going to be able to use to answer questions associated with water resources systems. So we assume no prior programming experience. And the other nice thing is we're using an implementation that is going to be in a browser. So there's nothing for you to install on your computer. I would say that for the purposes of the project, you know, if you want to go a little bit more hardcore with your data analysis, you can certainly implement a Python, you know, implementation that is not in the browser, but you won't necessarily be required to do that for homework and that kind of thing. So we're going to be teaching a Python that is pretty common and it's kind of scientific computing using packages such as pandas. I don't know if that's the right way to pronounce it, that's used for data frames and for other types of data analysis. This is going to allow us to organize our calculations similar to spreadsheets. We're going to be putting things in columns and manipulating them in that way. We'll be also using NumPy, which is a MATLAB-like package for numerical calculations. One of the things that's nice about NumPy is that the calculations for loops and that kind of thing are much faster than pandas. So you'll kind of see that we'll bounce back and forth between these two different libraries. The libraries are related to each other anyway. And then we'll also develop plots using things like matplotlib. There are packages that people have developed out there for particular things like numerical optimization. Platypus was developed. There's packages for trade-off visualization. And so with only a few lines of actual code that you have to write, you know, you'll be able to do a lot of different things. As I mentioned, we're going to be using a platform called Google Colab, which is an implementation of Jupyter Notebooks. And so Jupyter Notebooks are another way to go. It's just that they require you to install Python on your computer, and the Google platform has a couple of other things in it that are convenient for our purposes. A lot of the libraries are already installed, and you know, there are also some bash commands that are supported and other types of helpers that are supported that are going to make our lives easier. A water reservoir is, there's a single water reservoir that has a particular capacity, okay? And at every day that that reservoir can maintain a particular amount of storage, okay? And so the reservoir also has water coming into it as an inflow, and it can release water in two different ways. The first one will be the delivery of water to a particular demand. So this city or some other water user is demanding a certain amount of water, and the reservoir can deliver up to the 100% of that demand, okay? And so that is one aspect of the reservoir's operation. The other aspect of the reservoir's operation is if in delivering that water, it turns out that there would be too much water, and the storage would go above the capacity, any excess amount of water will go into spill. Okay, and we're going to see in a second like how there's aspects of this that are realistic, and then there's aspects of this that are less realistic, okay? So in order to look at the performance of the reservoir then in this situation, we need to solve the mass balance of it. And the way that's going to work is, let's just take a look at what happens at a particular time step. So there's a certain amount of water that's in the reservoir in storage. So storage sub T, inflow coming in at that time step, inflow sub T. And then there's releases that occur at the same time to spill and to delivery. So spill and delivery are going to reduce the amount of storage that you see at the next time step. So storage T plus 1 is going to equal storage T plus inflow T minus spill T minus delivery T. And you'll see in the textbook, there's different, kind of iterations of the same equation, but they all kind of do that. The change in storage is equal to the inflow minus the outflow, okay? And so, what we're going to do then is we're going to have inflow for all time, okay? And we're going to have demand for all time, right? We're going to assume that we know the demand. And then we're going to have to solve how the storage changes, how the spill changes, and how the delivery changes as a function of time, okay? And we'll do so using this equation. So what are some caveats, and what are the types of things that we're going to explore as we go further in the class? Well, the first thing is that we're not going to be calculating any evaporation or any other kind of losses, both from the storage in the reservoir as well as no losses as far as conveyance of the spill and the delivery and so forth. One of the rules, we talked at the beginning of the class about the fact that we have to structure these quantitative decisions, and we have to make decisions about how the reservoir is operated. And so one of the decisions that we have to make is, how do we control spill? And so here it's just spill an infinite amount of water if you can, just if the storage overtops the capacity. In reality, you're going to have much different spill characteristics. You might actually have situations where you're releasing more water, even if you haven't met the demand or what have you, because spill is going to be a function, say, of storage, of the elevation of the reservoir, and so forth. And we'll add all of those details as we go along. But for now, we're just dumping the water if we need to. And finally, we have another rule that has to do with what goes on with demand. Okay, and so the idea here is that we are going to always attempt to meet the demand. So in other words, if you have enough water in the reservoir, you meet the demand fully. Let's say that there's less water in the reservoir than there is demand, then you're going to drain the water and basically make the delivery as close to the demand as possible. What we're going to be carrying out when we start this reservoir behavior investigation is, one of the first things we're going to look at is what's called a critical period analysis. And we actually went back into the literature and looked up one of the first applications of this in the academic literature, which came from a paper in 1969. And the way that they introduced the concept of critical period analysis in the first place was they acknowledged the fact that a reservoir can be sized in a number of different ways. This goes back to the hydrologic inputs that we talked about on the first day, where you have this input of water. Where does that input of water come from? Okay, so there's this given sequence of historical or observed flows. That's one way to do it. And then there's synthetically derived sequences of many possible flows, which in some respects is the kind of more modern way to do it. So they were kind of exploring whether or not you can use the historical record to get an answer for sizing a reservoir that would be the same as if you were to do it many times with these synthetically derived sequences, given, of course, the fact that in the old days, it was basically impossible to be able to actually derive a lot of these sequences in a sort of efficient way. So what they did was then they said that this critical period was defined as, quote, the period of time in which the historical hydrologic record would have been most critical respecting the demands of the system. So in other words, if you carry out this type of thing where you're, meeting your demand at all costs, then you get to see sort of what the storage trajectory of the reservoir, how it behaves, and sort of what is the time period that caused it to drain and so forth. Okay, and so I intentionally sort of show you the quote first, because the quote hinges on this idea that it's almost a vague, like the most critical time in the historical record, and that's that, right? And so how do you interpret that? We're going to see that there's a little bit of disagreement on how that is exactly interpreted, which is kind of interesting. So you originally assume that the reservoir was full and that the period is like, it goes from full to empty and then full again. And the reason why they did that was because they were trying to stress the system, and they were looking at increasing the demand or the release level such that those periods would be kind of more and more severe. Okay. It's interesting that from a historical perspective, a lot of times there are concepts that were well-intentioned, say, when they were first introduced, and then people kind of ran with them and, maybe put too much emphasis on them, when you can kind of see right away that this analysis, as we're about to do it, is going to have some flaws associated with it, right? It's going to assume that the historical record is, will repeat itself exactly as you would see it. In other words, the past is going to be representative of the future. So just kind of a randomly selected set of, of documents out there. There was a basin study that was done by Reclamation in California, and it says that, so this concept of firm yield, which is also related to the critical period, a quantity of water that is projected to be available on a reliable basis given a specified level of risk during a critically dry period. Okay, and so in that study, that's how they defined it, like by this California law. But then Reclamation defines it as the maximum quantity of water that can be guaranteed with some degree of confidence during a specific period. Okay, and so you can see that even in the definition of the terms, there's already some uncertainty as to how it's defined. The second example is from the EPA, and here this is a water quality kind of thing, and they call the critical period a period during which hydrologic, temperature, environmental flow, and other such conditions result in a water body experiencing critical conditions. And then a 3-year period is the critical period. Notice also that it has to do with, like, that can be the way that the term is defined, but then also look at how they select a particular period. They're going to select 1991 to 2000 and then pick that 3-year period from within there. So I think that the moral of the story here is the fact that it's not enough, in my opinion, in my professional opinion, to just say, I'm going to calculate the critical period. It's much better and more precise to say, given a historical record from, the beginning to the end, the critical period was defined as a period of time in which the reservoir went from full to empty to full again. And you would need to say all those things, and then people would know, exactly what you meant. Okay. So, in addition to the uncertainties around the way that the term is defined, we're going to talk, when we get to the hydrologic input portion of the class, we're going to talk about this idea that the field has really come to terms with the idea that the past is not the best source of information about what's going to happen in the future. So, even in this little blurb here, it says that the systems have been designed under stationarity, the idea that natural systems fluctuate within this unchanging envelope of variability. and that has been called into question based on things like climate change. So, I think that you could say that the analysis we're about to do is one marker of how well the reservoir will perform, but it's likely that the performance in the real world could be maybe even worse than what we're going to say, and it's certainly going to be different. Okay, so what we're going to do kind of is start by looking at the historical record, but then gradually adding in other types of uncertainties and sort of seeing how the system changes. And we can keep using this same example from today and then just adding more to it as we go along. You are going to see on Canvas a link to this file, okay, that has blanks in it. And so you can see that there's a couple of places that I want you to kind of follow along and type into. So what I'd like you to do is grab a copy of this file, and then basically like you'll be able to open it up in Google Colab and save a copy of it for yourself, and you can follow along with me. And then the nice thing is that you will also then be able to you'll have that to modify later. And so when you have homework problems, you're going to get a copy of the homework in a file like this. You make a copy for yourself and then fill in the details. Okay. And so I've just renamed it. So imagine that this is the one that I pull from, from online. You can go into the file and save a copy in Drive, and then it'll allow you to save it. And then I change mine to in class just so that I can type and save a copy of what I've done here. Okay. So if you haven't used Jupyter Notebooks before, they're really nice, and they're really flexible. So the way that it works is that you can actually, when you mouse over the middle here, you can actually see that you can add blocks. Okay, and so like if I had a text block, I can say, I can add links, I can do different things, and I can say, this is an example of Python from CVEN 5393. And notice that this, uses like a basic markup kind of language. So if I hit bold here, notice that I can change the formatting here, and then it'll actually show me what it will look like after it's kind of rendered over here. And then after I do that, then I can just mouse away from that block, and that text will be nicely kind of displayed here. Okay. So there's two different types of blocks. There's text blocks, and then there's code blocks. Okay. Now, this is code that I've written, and notice how there's like a blank bracket here, and there's a little play button. So the blank bracket indicates that I haven't actually executed this yet. Okay. And so therefore, like I haven't actually done anything yet. I've just written the code, I haven't executed it. The notebooks allow you to kind of run things like sequentially. So you run this block and then you run the next block and so forth. And it'll actually remind you like the order in which you ran the blocks. You kind of assume that things go from top to bottom, but you're not required to have them go top to bottom. And so that can kind of get confusing, and it'll tell you sort of in which order it executed things. Okay, so a lot of the times what I'll do is I will be working, and then I will kind of add in a code block and like add something to kind of test things out. And we'll probably play with that a little bit here today. All right, and so when you get started, then you also have like some tools over here, like this variable inspector is not always included in Jupyter Notebooks. And so that's one of the nice things about this Google platform and so forth. Okay, so you actually have a file system. Now the file system is only temporary. So when you upload a file into here, then it's only going to last for the session. It's going to warn you about this. And so for the purposes of what we're doing, like I think it's okay for us to just upload things every time we start working. And so I'm going to do that. Basically, I'm going to go into my file structure, and there will be a copy of this Excel sheet on Canvas. So find it on your computer, and I'll show you sort of where it is on my computer. Okay, so I have a folder here, just somewhere on my computer, in which I have a copy of the Excel sheet that is going to be used as the input for this. And yeah. So here is the Excel sheet that is used, and I'm going to open it. And when I open it, it's going to put it into the file system here. And it's reminding you that you're going to have to do that every time you start a new runtime. Okay. There's fancier ways of making it persist, but this is going to be good for our purposes. Okay. So now this is going to be there. Okay. Now, if I go, I have some lines of code that are already written here in the version of this that I gave you. And what is going on here? So you're importing these different libraries. As you'll recall from the slides, we have these different libraries that are used to help us do different things in scientific computing. And there's two different ways that are shown here to import things. I'll start with this one. This is just importing all of the functions in the system library and making them available to us. And then we're also using these aliases. So we're saying that we're going to put in the NumPy library, but I'm lazy and I don't want to type out NumPy every time. So I'm going to use NP to stand for NumPy and then PD to stand for pandas. Okay. So if I want a function that is included within pandas, then I put PD dot the name of the function. Okay. And same thing with NumPy. All right. So let's write our first code. The cool thing is that there's actually a one-line code to basically read this Excel sheet and put it into a data frame. You know, one of the things that you'll learn about data frames is that they are very similar to spreadsheets. So what I want is a data frame that's going to be titled just that the title that I'm going to pick, I can make it be titled whatever I want, but I'm going to have a title that is going to indicate that it's daily data. So I'm going to call it daily, and then I'm going to use an underscore and call it DF. That is just a way for me to remember that this variable is indeed a data frame. You don't have to call it underscore DF. It's just sort of a convention. When you are looking up examples online, you're going to see that they'll give you an example and they will they'll often just use the variable name DF. Okay, so this is actually a helpful thing for me to show you, like if I Google, like I literally Google, like read Excel into pandas. All right, and I look at the results. Okay, you can see in the pandas documentation. All right, what you really want to do is that, and I mean, if you would see me when I'm developing my course material, like I have 8,000 tabs open, is that it's really important, like here at the very beginning, to be able to understand how to read documentation. Okay, so like I have this function that I want to learn about. So in order to call it, you have the name of pandas, which for us is just PD. So pd.readExcel. And then it's going to tell you the parameters, and it's going to tell you the parameters that are required and the ones that are not required. Okay, and so you can see that some of these will have these default handles in there, which means that if you don't say anything, it will default to a particular value. Okay, but the first parameter seems to be the only one that's actually required, which is just the path to the file. Okay, and so we're just going to write a quick command that's going to give the name of the file, and then we're also going to use the first column of the file to be saved as a special column called an index. Okay, and that is going to allow us to use the dates to index our data. This is the data. It basically has a date. It's called time here, and we could rename that if we'd like, but we'll just keep it like this. So it's just the date and the year, and then the average flow for that day in meters cubed per second. And that's all it is. Now, if you were doing this calculation in Excel, what you would do is you would start adding columns to do the different things that you needed to do. And we're just going to do that with our data frame. Okay. So the other thing I just wanted to show you about the documentation real quick, there's all these different options that you can give, but you want to always go and look at the examples, okay? And so you see that the easiest thing, and this is exactly the way we're going to do it, is we're going to give it the name of the file, and then we're going to say that we want the index column to be, so we're going to use 0, okay? And that's going to mean that we are going to want the first column to be representative of the index column. So Python is what's called a zero index language, which means that the first item in the list is actually the 0th item in the list, okay? All right, so we're going to save our output in this daily df. All right, and so I need to access this function, so I'm going to say pd.read_Excel. Now, the cool thing is that if you notice, like when I put my round parentheses here, it's actually going to show me the usage case of the function, just like we saw in the documentation. And so it's going to say that I need the actual input output, and then that's just going to be the name of the file. So Des Moines River flow.xls. Keep in mind that it's case sensitive, so you know the F isn't capitalized, and so I'm not going to capitalize it there. And then I'm going to put a comma, and then the second command is going to be this index call. And notice how the collab is actually smart, and it knows that that's one of the parameters in that the function can take, and so it's going to do that, and then I can put 0. Okay. All right, and now this block is ready to load. What it's going to do is it's going to run everything that's inside this block. So it's going to be the 3 import commands, and then it's going to populate this variable, and then all that stuff is going to be available in memory to us to do later on. That's why it's helpful to start from the top and go to the bottom. You're not required to do it that way. The only thing that's required is that within a block itself, you're going to go from the top to the bottom. Okay, so we'll just hit play. And then the green check mark is a good sign. That means that it completed successfully. Okay, and you can know that that's true because when you go to your variable inspector, you'll see that this successfully populated. And the cool thing is that you actually, when you mouse over this, it shows you a result that actually looks a lot like a spreadsheet, right? You have time as the index, and then the average flow. Okay, so some cool things that we can do actually is that so I just hit a button to create a new code block. And so if I just put in the name of this data frame and I hit go, it actually shows me, you know, a representation of it. And if you hit this little magic wand, it'll actually put it into a table, an actual table where you can look at every single item. Okay, which is super cool. If I want to get rid of this output, notice that I can mouse over here to this little icon, and I hit the X, and it gets rid of the output. Pandas also has a bunch of stuff that's built in, and so if I want to create a plot of the data, I can actually operate on that data frame as if it was an object. So I can go .plot and look at what happens. It actually just plots the data right there. Okay, so super cool, and it'll plot every column basically in its own line by default. Okay, so very neat. And so what I'll do is I'll actually you know, I have some choices. It's, you know, like me calling this function is really not going to do much of anything, but if I wanted to keep it, I could kind of document my work. And this is also something else that I should mention, is that notice there's this green text here that is highlighting, you know, like what I'm doing. These are comments, okay? And they are not executed at all. All it is just text. So if I want to add a comment, I can, you know, just like this. And so I can go and I can say a plot of the data, And then that way, I will remember sort of what I did. Notice how in the code that I've given you already, like I've really tried to comment. In a notebook, it's even better, you know, well, better, I guess, is like in the eye of the beholder. But if you actually add a text block, you know, you can actually add even nicer kind of explanations of what you're what you're doing. And so you could you can also write yourself a little text block. Okay, and in future examples, we'll probably have more text blocks. You know, but for the time being, you know, I also just kind of wrote things in comments this time around. All right, so we've already taken a look at the data frame, and we see that the average flow in cubic meters per second is in here. Now, when we go to the slides, right, everything is here is just in terms of volume units. And so what we're going to do is we're going to just assume that that average flow rate over the course of the day, you can just integrate it and it's going to be a volume. Okay, so we'll convert from cubic meters per second to a volume unit for the purposes of what we're doing. So, you know, it is possible for you to do that conversion by multiplying by the numbers every single time. So if you had every number that you could do, you could go in and you could multiply it out. But if you're going to do a calculation many times, it's better for you to put it into a function, and that way you can just call the function a bunch instead of calling, you know, having to type that out. Because then if you want to change the function, you know, you only have to change the function one time, you know, because you keep reusing the function. Okay, so let's write our first function. I've already written a comment of what we're going to do. The flow within the Excel file is in a rate, cubic meters per second. We want to convert it to a volume, millions of cubic meters. One of the things that you'll notice about this coding style that might be a little bit different than what you're used to is that you'll see people, and even if you were to look at the MATLAB version of that was originally used for this example by Professor Stefano Galelli, he uploaded it to this repository of course information for water resources systems. His original code is like X equals this and S equals that and that kind of thing. And there's nothing wrong with doing that, but nowadays, you know, when we have big monitors and lots of memory and all that kind of stuff, you know, you can actually, like, instead of calling something S, you can call something storage. And that way it's easier for you to remember what it is versus just calling it, you know, S. And so you're going to see that the lines of code that we write are going to have more kind of letters in them or whatever. But I think that there's a good reason for that. Okay. And you know, you do things in coding really to help your future self, you know, like you want to be able to read it. You want your partners to be able to read it, like when you're working with people, but then you also want to read it. And you'll see that my variable names are kind of long. All right, without further ado, let's go. I'm going to call the function. And again, in that spirit, I'm going to use a somewhat long function name. And the function name is going to say exactly what it does. And it's cheating a little bit because it actually sees in my example already that like this variable name is used. And so if I just want to do an autocomplete, I can just click on that button and it's going to continue writing it for me. But I'm just calling the function exactly what the function does: convert CMS to MCM. Okay. Now, so that is the function name. It's what they call a user-defined function. The functions always start with the word def, and then what's inside the parentheses is what the inputs to the function are. So notice up here you had read Excel, and then you had some inputs that are in these parentheses. We're defining the inputs, so we get to say what those inputs are. This is only going to have one input, and it's going to be just some value. Okay. Now I am using a bit of a generic name for this value on purpose because I want you to remember the fact that this this variable only lives inside of this function. Okay, so like I put the variable in here, and then like the only time you're ever going to see the word val is just in calculations that have to do with what's going on inside the function. Okay, and so I can have a colon. Okay, so then the colon indicates that I'm going to start a block. When I hit the enter button, notice that the cursor is indented, and that's important. Python requires you to indent content that lives inside of a block. And so it knows what the hierarchy is of whatever you're doing based on how much it is indented. If you, let's say that you had something that's on the same level as something else, it has to be exactly, say, one tab. And then you go down and then it's the same tab. If you even have one extra space, it's going to yell at you and it won't work. And that's something that's probably the hardest thing to get used to relative to something like MATLAB or even R, where they're not as, they do not require you to maintain such a strict sort of indenting routine. But it's nice because it helps you, it helps the code be readable and that kind of thing. There's two different ways to do this. I'm going to kind of show you one way, and then I'm going to simplify it for you. So inside of this function, I can create a variable called result, and then I can do the calculation. So I can say that in order to do this conversion, I need to take the value that's inside that we're assuming has units of CMS, and I multiply them by 24. Now I'm using the dot to indicate that I want 24 to be a floating point number. You don't really need that here, but sometimes, like say for example, when you're dividing numbers, if you divide like 1 divided by 3, that's going to assume that you want a fraction, or that you want like the integer portion of that. So it's going to mess up. If you want it to be 0.33, you need to give them floating point numbers. So anyway, so 24 times 60. Again, here I don't think it would matter, but I'll just do it for completion's sake. Times 60, okay, divided by 1 e raised to the power of 6. Okay. All right. So in other words, you have cubic meters per, and so actually what I'm going to do is I'm going to write out like the conversion just so that we, for completion's sake. So if I have cubic meters per second, okay, then I want to, and actually there's probably a way to do this, but that's beside the point of what we're trying to do right now. So if I have meters in the cube per second and I want to convert it, right, I want to get rid of this, I want to convert it to millions of cubic meters. I am going to assume that, it's operating over the number of seconds in a day, right? And so if I say that there's 24 hours in a day, right, and I say that there's 60 minutes in an hour, and then I say that there is 60 seconds in a minute, right? Then the seconds is on the top here and on the bottom there, so that cancels out. And so we're left with cubic meters. And then the last thing that I want to do is I want to convert cubic meters into millions of cubic meters, right? And so then I divide. So if the unit that I want is like millions of cubic meters, right? Then I divide by 1 times 10 to the 6th meters, okay? And that's the final part. So multiply by 24 by 60, and then divide by 1 raised to the power 6, 1 raised to the power 10 to the 6th, okay? And then you get the conversion, okay? Now, if I just quit what I was doing, all right, what would happen? Well, like if I didn't do anything else, then this calculation would be done inside of the function. and then nobody would know about it because there's no way to like get the result of that function out of the function. In order to do that, I need a return statement. So I just return the value, the variable that I created there, and then that is going to be the result of our function. So when I hit play here, what that's going to do is that's going to put the function that I wrote into memory and allow that function to be called now because it lives there because I've executed this code. And so to test it out, then I can just go in and I can look at, or I can call the function and use it to do my bidding, you know. So if I go back and I look at, you know, if I go back and I look at the data that I'm working with, and I know that on this particular day, like it's 117 cubic meters per second or whatever, I can say, like, I can basically say, all right, I use the name of my function and then I say 116 cubic meters per second. And then when I hit go, it's going to call that function and it's going to give me the result of what that is equivalent. So 116 cubic meters per second on an average flow would then yield 10 million cubic meters of volume, okay? And that indicates that the function is working. It just prints out the answer. It prints out what that was in that result. I can also save it to a variable like this. Now, when I save it to a variable, it doesn't print anything to the screen, but notice that it's created a new variable in my variable inspector that has the value that that's stored within that variable. Okay, and so that then I can use to do other things with. Okay. All right. So remember how I said that when we would be doing this, like if I were to go into here and I would want to, I would want to do that conversion. I need a variable called inflow, and I might put in a column here that's called inflow, and then I can write the equation. I can say B2 is times 24 times 60 times 60 divided by 186, right? And then I get the answer. And then I can populate it. So what did I do there? I created a new column, and then I populated that column with this formula, okay? And so we basically do the same thing here. So on the left-hand side, I'm taking my data frame, and I'm putting brackets, and I'm putting in that I want to create a new column that's going to have the header inflow. So that's what I'm doing over here. And in Python, you can just add in a new column at your leisure by doing it this way. And then I am going to populate that column with the result of my function. And the input to my function is actually going to be a whole list of numbers, okay, from the data frame. Now there's one complication, and for those of you who took 5423 with me in fall of 22, I did not teach you how to do this, and I think that was probably a mistake on my part. You know, when you are operating with data frames, it is a really good practice to convert them into NumPy arrays when you're doing numerical calculations with them, because it's a lot faster. And so what I did here was I just took, what this is doing is it's taking the column from the data frame, basically converting it into NumPy, and then that then is the input to this function that I wrote, and then the output of the function that I wrote is that inflow column. Okay, so I do that, and then this next column that I'm creating is really easy. I'm just putting the number 2.5 in all of my demands. That would be equivalent to me going in here. I go into demand, and then I just say 2.5, and then I just drag down. Okay, so Python knows that if you just put a single number in there, it's going to fill every value of the every row with that number, just like I do when I double click my mouse there. Okay, again, nice to do things in small chunks. So we're going to do this, and then we're going to just hit go, and it's going to, it changed the shape of my data frame and added 2 columns, see? And I can even mouse over and look that the output of what I'm doing is the same as what I did in Excel. All right. The next function is written for you. So it is a reservoir simulation. And what's going to happen is this is again going to be equivalent to this idea that you're going to go into the, you're going to go into your rows, you're going to do something, kind of drag it down. And at the end of the day, you're going to be saving more columns that are going to have other information in here. So notice that a data frame, any kind of generic data frame, is going to be the first input. And at the end of the function, you're going to return that same data frame. So notice, spoiler alert, you can see that there's going to be extra columns of that data frame that are going to be added. And then, so the data frame that you have when you are done with this is going to be kind of new and improved relative to when you got started with it. Okay, so the data frame is the first input, and then there's 2 other inputs. One of them is the initial storage, and then the storage capacity is a 3rd input. And that should be all of the information that you need to be able to do that simulation. Again, what we're going to do is we already know all of these inflows. We just need to solve this equation basically and give our deliveries and our spills and so forth. And then at the end, we're going to have the things. I wrote it down, so I should just follow what I wrote down actually. Okay, so now you are not required to write these comments, but it's always a good idea when you have a function to, you know, to put in what the inputs and the outputs are. So the data frame that you put in here is going to have an inflow and a demand for the entire time series. Everything is going to have the same units, so it's volume units. Notice that it doesn't actually matter. I don't believe that there's anything inside this function that is going to be relative to the fact that we're working in millions of cubic meters. It's helpful sometimes to make things as generic as possible. So if you can help it, you know, just make the units consistent, and then if you have different units, it should still work. Okay, so inflow and demand in all time, and then the initial storage that's going to happen at the beginning of the time series, as well as the storage capacity. Okay, then the output is going to be inside of that data frame. You're going to have storage, delivery, spill, and outflow for all times, where outflow is just going to be delivery plus spill. Also helpful to document the fact that this is a really simplistic operating scheme that we have here. It's just going to be, release all the water possible to meet the demand, even if that means that the reservoir will drain. Spill occurs if that storage that you calculate exceeds the capacity, and then no capacity constraints for releasing spill. If you flood downstream, this is going to allow that to happen. All right, notice that in our function up here, we pulled out a NumPy version of the column that we're working on, and so we're doing that here. So I'm just saving a copy of this, a NumPy array called inflow that is going to be taken from the inflow in my data frame. Same thing with the demand. Okay, then we can leave these guys alone, and we can just operate on these copies that we've made. Similarly, I'll save a version, or I'll save a variable n that is the length of the inflow series that I have. And not unlike you might have learned in MATLAB, we're going to actually create ourselves new variables just so that we know how long everything's going to be when we actually do the calculation. In NumPy, you're not allowed to index something unless it already exists. So this is just basically saying that we're storing zeros in all of our variables that are the length of n. Okay. So these aren't very interesting right now, but they're going to be populated with stuff as we go along. All right, and so now we're ready to work. So we're starting at time step 0. Again, remember that is the first time step because of the 0 indexing. And so the storage, the initial storage, is just going to be equal to the parameter that we put into the function. So storage, the first storage in the list is going to be equal to the initial storage. So next we're going to do a for loop that's basically going to calculate things one at a time, starting at 0 and going to n. Now, it is a bad idea to do this directly in the data frame itself because indexing data frames is very slow. But because we're working with NumPy arrays and NumPy is used to doing these kinds of things, this calculation is going to go very quickly. So basically, I will begin at 0, and then all the time that this block, that the control is in this block, I is going to be 0 until it gets to the bottom of the block, and then when it goes back up to the top, it'll be 1, and then it'll be 2 and 3 and so forth. Okay, so the first thing that I'm going to do is create myself a little temporary variable that's going to calculate how much water is available right now. So the available water is equal to the inflow, which we know, plus the storage, which we also know. We know it at the beginning because at the very beginning, it's going to be the initial storage. Later on in the simulation, like for the next time step, we're going to later calculate what the storage of the next time step is. So by the time we get to here, we will know what the storage is. So you look at the amount of water that you have right now, inflow and storage, and save that as a temporary variable, available water. I am not keeping this because I don't really care about it. I'm just going to use it as the test for what to do related to meeting my demand. Okay, so if I have enough water to meet my demand, if the available water is greater than the demand, notice this is another one of those blocks that has indenting and a colon. So if this condition is true, then execute this part of the block, which says that the delivery that I'm going to have is going to be equal to my demand. I have enough water. My rule says that I can just give that water away. And so delivery is going to equal demand. Otherwise, we know that the water there's not going to be enough. And so we're only going to deliver inflow plus storage. So whatever we have left, we're going to give it away. Okay. Now you can see that this could be a problem sometimes because maybe, that demand is not as important. Maybe the reservoir is not actually able to release all the water to make it completely empty, but we have to walk before we run. Okay, so those are the only two conditions that you need to worry about for delivery right now. Now, right now, okay, if we go back to our mass balance for a second, we're going to see that we're actually almost done. Ignoring spill for a second, you have a certain amount of water. Water's coming in, and then we're going to take water away. If the demand is really low and the inflow is really high, we have a problem potentially, because if the initial storage is equal to the capacity, if the reservoir begins the simulation full, then the large amount of inflow is going to cause the reservoir to overtop. And even if you're delivering a certain amount of water, maybe you're not delivering enough and you could have problems. And so I have taken note about the fact that I want to deliver this amount of water, but I might need to release more water based on the fact that maybe I have to spill it because of the capacity. Okay, and so that's what's going on here. So again, I'm going to take a temporary variable and I'm going to say, temporarily, I want to know how much is going to be in storage for the next time step. That could be storage, the storage of the current time step plus inflow minus delivery, right? But if this is too big, we need to do another test. Okay, so if that is going to push it over the limit, then we're going to need to spill water. Okay, so if the trial storage is greater than the storage capacity, then we're going to spill the extra part that's over and above capacity. Let's do this one at a time. So this block, and you can tell that these two things are happening at the same time because they are at the same level of indenting. So if the trial storage is greater than the storage capacity, then do what's in this part. Otherwise, do something else. So otherwise, this implies that the storage is below storage capacity and we don't have to spill anything. Okay, and so we don't have to spill anything. Up here, we are spilling something. Now, either way, we need to get ready for the next time step. And so just ignore the fact that there's another if statement here. If you just look at here, it's like next time for storage I plus 1, then realize that like up here, if we spilled water, then what's going to be left is going to be simply the capacity. Okay. Otherwise, this calculation that we did up here is correct. And so we can say that the storage is equal to what we thought it could be. Okay. Now, that's great. But if you did this without another if statement, you would get an error, because if you think about it, there's 34,563 items in this list. When you get to the bottom of the list, you're going to try to save the storage for next time, but everything needs to have the same number of rows basically in our data frame. So, you know, you're not going to want to save that very last one. It's going to be the end of the simulation, and, you know, it has to end at some point. So, you know, that's what you're going to do there. Okay, so that's why we say if I is less than n minus 1, you know, we store this. Otherwise, we just don't do anything. Notice that, so this demonstrates the fact that an if statement doesn't have to have a companion else. You know, it's allowed to have one, but it also doesn't have to have one. Okay, so much ado about nothing. The point is that let's just go back and quickly review what we did. So inside of this loop, for all time steps going from 0 to n, we start by saying, I have inflow plus storage to be able to give away. If that's enough for my demand, then I deliver what my demand says. Otherwise, I only deliver what I have. Okay. And so I'm done with the delivery variable. Like, I've saved that and then that's it. I'm not going to do anything else with that. Then I need to worry about storage. So I say that initially, I think that the storage is just going to be simply equal to what it is now plus what comes in minus what goes out. Okay. But that might push me above our limit. If it does, then I need to add an extra variable that's called spill, that's going to give me, that's going to cut my storage back down to where it's supposed to be. Okay. I do that if I have to. Otherwise, my spill is just going to be 0. And then I need to update the storage for next time. Notice that it's storage t plus 1 equals this stuff. And I only do that if I'm before the end of the list. All right, the last thing is just a bookkeeping thing. We're just storing an extra variable called outflow, which is just the sum of spill and delivery. Now notice the indenting here is really important. So this indenting indicates that, like, when we're here, the indenting, this level of indenting is over. So it knows that it needs to go back up to the top of the for loop and increment I, you know, and go again. So when I equals 1, remember that we would have stored the storage value the last time. So that's going to be there for us. All right. And then we're going to be able to work again. So we know what the inflow is because we knew inflow in all time. Storage we calculated from last time, and then we just repeat. Demand we also know. So remember that, like, inflow is known, demand is known, and storage came from last time. And then everything else is updated. Okay. So that indicates the end of the for loop here. And then before we leave, we just need to save our work back in our spreadsheet. Okay, and so we're just creating these columns for the data frame and then popping in the NumPy versions of those things that we just worked on into the data frame. Again, if we didn't have this last one, then if a tree falls in the forest and no one hears it, does it make a sound? You know, nothing would happen. But when we return the data frame, that means that we can, you know, save our work into a copy of that data frame. All right. So hopefully this will make some sense when we actually call it. Okay. Again, you know, the thing that's nice is that when you write functions like this, the user, quote unquote, the person who's implementing this simply needs to know how to call this thing, right? So we just need to know sort of how to use our function prototype to actually to do some work. Okay, so if we know this, then we're going to have a good day. And remember that we have this data frame that already has inflow and demand in it, so we're almost there. Okay, so now let's insert the code to actually use the reservoir simulation to do something. Okay, now I'm going to so there's kind of two different ways of putting the information into the function call, and I'll show you what both of those look like. Okay, so remember that we have daily df, and that's in memory, and we were able to use it. So like, I'll just start building this call. So I want to put the name of the function. That's so that Python knows what function I want. And the first argument, notice again, it shows us, it's very helpful. It shows us the three things that it needs. The first one is that it needs the data frame. Okay, and so our data frame is called daily df. This function is generic. So if we have other data frames later on that are, you know, that have different names, we're going to be able to pop those in as well. Okay, so daily data df is the first argument. And then we need to give it initial storage, and we need to give it storage capacity. So in the prompt that this problem is based on, you know, the initial storage is 750 million cubic meters. So we know that. Now, like, we also might have that information from some other calculation that we do or whatever. And so I can actually like, I could create another variable. If I could spell correctly. Keep in mind, by the way, that like spelling and uppercase, lowercase are all preserved here. So like if you spell a variable name wrong, you're gonna have to spell it wrong all the time. And you'll actually see that where things will be spelled wrong. So just be careful with your spelling. And that's part of the reason why tools for authoring things are really nice, because they kind of guide you along. Like if you've made a mistake, it'll tell you. But anyway, I'm just going to save, I'm going to save this as a variable, and notice how I can, like for the third argument, I could put in a variable here if I want to. See, so this is the same thing. I can type it in and hard code it here, or I can actually pass in the variable itself in there. But both ways are okay. Now, if I were to just do this, think for a moment about what would happen. The data frame that we create is going to, it's not going to have any place to store, because like when we modify it, right, we're going to be modifying it, but like we need to actually return it for it to do anything. And so to make a long story short, I need something, I need something on the left-hand side of the equation for the output of this function to be stored into. And notice that it's going to be stored actually into the same variable that we put into it in the first place. Okay. And so we'll do that, and then let's see how we do. We get an error, fun fact, and it says that reservoir simulation is not defined. All right. The reason why it's not defined is because if you look up here, see how this guy has like a blank space next to it. This was not a plug. I genuinely made this mistake just now. I forgot to basically put this function into memory. I need to actually run this block of code first. Now notice when I run it, it's not going to look like anything happened, because when you define a function, it's just like buying a tool. It's almost like buying a treadmill Like the treadmill won't do anything until you use it, but the treadmill actually has to be in your house, right? So similarly here, when we run this code, it makes this function available to us. So I did that. Now this down here should work, hopefully. And it does, okay? And so we can see the result of this. There's a couple of ways that we can see it. So now the old copy of daily DF only had 2 columns in it. Now daily DF has 7 columns in it. If I want to look at this, there's a couple of different ways I can do it. If I just put in a little block that says daily DF and I hit go, the Python environment is going to actually like give me this nice kind of sanitized way of looking at it. There's also some other built-in functions that are really kind of nice. One of them is called head, and that just shows me the first few rows. Okay, see that? So it's a really nice format. If I do this without the command, then it'll just show the whole thing. Okay, but you can kind of see then that it did populate our spreadsheet, basically, or our data frame, just like a spreadsheet would. So the other thing that I can do is I can actually plot individual columns, kind of like we did before. Okay. So for example, we can access an individual column using those brackets. So notice that if you're used to MATLAB or other types of like matrices, you can see that like you might have to remember that storage would be like the 4th column or something. The nice thing about here is that you can actually access the columns by their names. So I can say I want storage, and I can say that I just want to plot it. And what that's then going to give you is a plot of the storage performance of your reservoir. And it's interesting, like even with a very simple rule like we had, you can see that there's some interesting behavior that's starting to have, where there are periods of this drawdown, and there are probably also some periods where there's spill. In fact, if we wanted to look at the spill, we easily could. So I'll just go in and I'll just take a look at the spill for fun. And there you go. Interestingly, like this could be an indication, this is very likely an indication that you would probably want some kind of more sophisticated management of the reservoir, because this reservoir is spilling like all the time. Okay, so maybe there would be a better way for you to manage the outflow of the reservoir. It's funny though, because even though the reservoir is spilling a lot, notice that there are still periods of time in which the storage goes down. So you would think that like it's kind of like a Goldilocks sort of thing, where even though there are lots of times in which there's plenty of water to meet your demand, you still have situations that stress this particular demand, where you have like that long period where it had to drain down to meet the demands. Okay, so so pretty interesting, and we'll do a lot more with these things as we go along. Okay, so in the interest of time, I'm just going to quickly kind of show you. I'm not going to go through line by line this next function, because we can kind of do it again when we're back together. But this is a function that basically tells you something about this transition, basically to do the critical period analysis. Like basically we need an algorithmic way for us that we can look in our brains and we can say like this period stunk. This period went from the reservoir being full to being empty, and then it took a long time for the reservoir to be full again. Okay, and so what we're doing in this function is we're basically creating a new data frame that's going to actually have different kinds of columns associated with it. This new data frame is going to basically take every instance where the reservoir started to drain, like from where the reservoir began full and then went down and then went back up again. So like when it goes from full to something other than full, back to full again. Okay, And it's going to save every time that that happened. Okay. And so, again, I'm going to kind of skip the calculation for now, but the point is that the input is the storage, a NumPy array of the storage record, and then the capacity. That is given as a variable because you may want to be able to do this analysis for other levels of storage if you wanted to, but for the time being, it'll be the same as the storage capacity we looked at previously. Okay, so those are going to be the inputs, and then it's going to yield this nice data frame that's going to have the information that you need in it. Okay, so all right, so then what do we have to do to run this function? First, we have to get it into memory. So I have to play that block in order for me to access that function. Okay, and then I need to get ready to actually put the information into it that I need. So it says that we need a NumPy array of the storage record. You may be thinking, you may be yelling at your computer screens right now, hey, why don't we already have that? We had that up here. Like we had that, we had that right here, for example, and we had this variable called storage. Why don't we have access to it anymore? Like you can't see it in the variable inspector. And the reason is because this storage variable was created inside this block, inside this function. And when something is created inside a function, that means that it only lives inside that function. Okay, it's almost like taking a piece of a Post-it note or something, going into a room, doing a calculation, writing it on the Post-it note, and then you leave the room and the Post-it note stays in the room. That's what a local variable is like. Okay, and so even though it looks like we might have had something similar to this, we're going to actually need to process this and get our information ready to go. Now, you could just pass in the toNumPy thing directly, but I'll just show you that we can create a variable. So now I'm going to create a variable called storage. Now that I'm out in the, in general, I'm not inside a function, this storage variable is going to last for me. So I have storage, and I'm going to say that that is equal to this row, or this column, excuse me, of my data frame, just that toNumPy thing. Okay. Now, when that command is called, then I'm going to have access to that variable storage. So I'm going to create a new data frame. Now remember that like this is the data frame that I'm going to create now is going to have a different row structure to the one that I was working with, because basically imagine that this period of time is one in which the reservoir drained. The first row of my data frame is going to be like, it's going to summarize this sojourn into failure, as they say. And then the next one might be like this period of time in which it failed. And then another one might be a lot longer. So the rows of this one are going to be each one of these different events in which the reservoir started to drain. That's why I'm calling it events, the events data frame. Okay, and that's going to be created when it is popped out of the function that I'm about to call. Okay, and my function again has a very verbose name that helps me remember what it does. That function is called transition from to full. Okay, and then the inputs to that function are the storage trajectory, and then the capacity that I'm caring about, which I actually have in a variable from elsewhere called maximum capacity. Okay. So I just call that code. Okay. And now we have a new thing. Now this is kind of cool. This is a really nice sort of summary of some of what's going on in this time series. So when I open this up, the way to interpret this is that starting at row 184 and ending at row 219, the reservoir goes from being full to being empty and being full again. and that lasts for 35 time steps. Okay. And if I wanted to, I could actually go in, and there's other ways of viewing the data frames and stuff. So like I could just save this data frame, for example, as an Excel spreadsheet, and then I could go in and I could actually look at the rows, in which each one of these events happened. And that's kind of why it's good to use tools that are kind of appropriate for what you're trying to do. Like nobody is saying that the ability to look at your data tabularly is a bad thing. It's just that you don't want to necessarily sacrifice the fact that you have to look at things like this for transparency in doing your calculations, like, because you can kind of follow this a lot better than burying a bunch of variables or a bunch of equations in a spreadsheet. But on the other hand, like you could take the results then and process them in other ways if you wanted to. Okay. But I digress. So the 0th event is when this happens. The first event is when that happens, and so forth. And when we go back to our critical period analysis definition, full, and then, I think I just said it, I didn't write it down, full to empty to full again. Okay. So one of the things that the original author of this exercise did is he figured that the maximum length of time in which it goes from full to empty to full again likely contains, or sorry, let me go back. What we're going to do very specifically, because what we were trying to find is like full to something other than full back to full again. We didn't actually check to see if the reservoir drained to being completely empty. Okay. And to basically like kind of show you what that would look like. This is one of the things that's like, again, you're not going to be invited to parties anymore because you're going to nerd out on all this stuff as you go along. So what we did was, when we were doing this calculation just now, so imagine that the reservoir is going full, the reservoir is full. So imagine that this is like full. Okay. And then we were saying the moment that the level starts to go down, okay, then we're going to mark that like this is happening. It started to go down. And then, it's doing whatever it's doing, and then it goes back up, and then we mark the ending of that period to be when it goes back to full. Okay. Now notice in this situation, and so we would call that like event 1. So we could say that this is event 1. And then when it happens again, we go in, and then that might be, just to use a different color, that might be event 2. Again, it goes from full to something to full again. Okay. And so this would be like event 2. So what we're going to do now is so we have like a record of all of the lengths of all of these events. But what we didn't do is we didn't check to see that the reservoir actually emptied. Now, you could actually say, you could create a metric and you could say, I want to know the longest period of time that the reservoir wasn't full. Like you could do that. But specifically for our critical record definition, we are trying to find the length of those events in which you actually did go all the way to empty. Okay, so like empty would be like right here, literally empty. And so you would need to check to see that there was an event that actually had that period of time where it was like, it went all the way down. Now, luckily, like, I think that it's somewhat safe in this analysis to say, even though it's not necessarily mathematically proven, that the longest event, let's say that this is like the longest event, E sub L, the longest event is going to include an event in which it actually drains, but that's not guaranteed. So the algorithm that Galeli wrote basically says that it's not going to care about whether it's empty, like inside this equation. You can just check basically that you can check once you have the longest event that it does actually go to 0. And then that is where you can say that that it's actually the critical period. So, you know, like this is maybe not completely accurate because it doesn't do that check, but the critical period length is going to be the maximum length essentially in that little table that we have. Remember this. So like the maximum of this column is the longest time that it's not full. Okay. So max inside the NumPy library gives us that, and what it particularly returns is that value, the maximum value in that list. But then there's also this argmax command, which gives you the index at which that happens. Okay, and so we do that, and then it tells us that the index of that events record in which this happens is the 7th event, and it has a length of 1809 days. Okay. All right, and so this ilock command is the way that you index a data frame, like by a row, just based on the number. And so like when we find index 7, it gives us the columns associated with that, so that the time period starts at 792, ends at 2601. The difference between those two things is 1809. Now, what I did here was I basically saved a slice of that daily data frame that kind of starts a little bit before and a little bit after that critical period, or what we think is the critical period, saved it into a new data frame here. Okay. And then the final thing that I can do, and again, this is a quick and dirty thing, but I plotted all the columns. You can see periods of low inflow. The point is that like the reservoir starts full and then kind of almost goes to empty, kind of refills a little bit, but then goes down again and actually hits 0 here in in between 1926 and 1927, and then finally finally fills back up. So that demonstrates the fact that this is indeed the critical period as we defined it, and thus, you can properly say that it's the critical period. Okay. So lots of cool things, and as we go along, we're going to do more and more with this storage time series, analyze why it is that things happen the way that they do, and calculate more different metrics that can then be used in different things like alternatives analysis, more complicated reservoir operations, and so forth. Okay, so take a look at the full code. You have a copy of the full thing as well. I don't have it up on my browser right now, but you can actually look at this again without having to type it all in, and play around with it and kind of get comfortable with this. We'll keep working with this example as we go along, especially in Unit 2. Thank you very much, and we'll see you next time.